I conversed with a couple of my co-workers that work in the math department, and they're good people. They agreed with me. So Tuesday, in like a week from this coming Tuesday, will be the start of your final. A week from this Wednesday, we will complete the final. If you happen to get it all done on Tuesday, that's good for you. God bless you. But the final itself will indeed end on Wednesday. Sorry, but if you guys are going to do your sprint across campus, good for you. Just make sure your final's done, or you come back and finish it or something. Cool. All right. So I was able to do a little.
Wait, does that mean that
No, we're continuing.
to do what?
Stop.
To do what?
Don't worry. I'm going to teach you how to gamble.
Alright, I'll come do that.
It's practical application.
Let's go to the final. Then we don't have to go to the final.
Send, check in with me, go to the library, and then you check out. That's the
Let's go
legal.
to Rico's.
That's on the way to the library? Okay. I'm in the wrong chapter. Okay, we are getting into our adventure of chapter 8. We started with 8.1, and we came across a couple of questions. Okay? And the questions were type 1 error, type 2 error. So this was a point of concern going, how does that even make sense? So I did what most people did. I went to the internet.
Skipped it.
I went to the internet, and I found, hey!
Whoa.
I'm hoping you're supposed to bring us ice cream sandwiches today. All right. So this is an attempt to clarify the type 1 and type 2 errors. I think that this that I printed off did a nice job. So this will give you a little review what I'm going to read to you, and then I'm going to go into the type 1 and type 2 errors. That'll make a little bit more sense. And then you guys, knowing you, will do what normal people will do. You say, why did you just say that in the first place? And it's because I didn't have that information at that point in time. Okay? All right, so in statistical test theory, the notion of statistical error is an integral part of hypothesis testing. Okay, that seems pretty simple, right? That statistical test requires an ambiguous statement of a null hypothesis. For example, this person is healthy, or this accused person is not guilty, or this product is not broken. The result of the test of the null hypothesis may be positive, healthy, not guilty, not broken, or may be negative, not healthy, guilty, or broken. Okay, are we okay so far? So they're kind of giving you three little things going. Hypothesis, this person is healthy. The null of that would be they're not healthy. The next example is this accused person is not guilty. The null of that would be this accused person is guilty, and so on and so forth. So if the result of the test does not correspond with reality, then two types of error are disguised, type 1 error and type 2 error. And this is where we got ourselves into a little like, whoa, wait a minute. Okay, so they say, this site says this, and I think this sounds pretty good. I mean, if I was able to read it with like my kindergarten reading level and understand it, I think you guys with your senior in high school, junior in high school reading levels or higher than that would be good. So a type 1 error, you guys ready?
Yep.
This is a false positive error. Okay, now before you're like, wait a minute. Okay, think about when you're talking about the medical community. Okay, there's tests out there like there's drug tests. So you can have a false positive, right? A false positive would mean that the person did not have any. If you're trusting to see if this person was on drugs, they got a false positive. They weren't on drugs, but the test for some reason revealed that there was a result of it. Okay, so it says a type 1 error occurs when the null hypothesis is true, but is rejected. Okay? I know that's still kind of squirrely, so let's see if we can clarify a little bit more. Let's say this again. A type 1 error occurs when the null hypothesis is actually true, but was rejected as a false by the testing. Okay? Let's see if we can clarify this a little bit more. Type 1 error, a false positive, is asserting something is true when it actually is false. Talk to me.
how do you decide, like, what, like, I don't know, what are the criteria for rejecting something?
I'm going to get there.
Okay.
I'm going to get there.
Sweet.
So, as soon as I get done with this, tell me if I didn't get there.
Okay.
Okay, but I'm hoping I get there. Yeah?
Are we still on 8.1?
Uh-huh. I'm trying to clarify the C and D examples. All right, so this false positive error is basically a false alarm. Okay, this false positive error is basically a false alarm. Think about what a false alarm means. Okay, is it possible that the fire alarm goes off right now in the school?
Sure.
Now, some people might say, oh, some silly kid pulled the alarm. Okay, or there actually might be something bad and we need to get out of the building. Okay, so it's like a false alarm, a result that indicates a given condition has been fulfilled when it actually has not been fulfilled. An example, erroneously, a positive result has been assumed. Now, this next little example I'm going to give you, I think, kind of will clear it up a little bit. You guys have all heard the term, you shouldn't cry wolf, right? Remember this? Okay, so this is what the examples go on. So this is kind of like where the term probably came from. Okay, it says, let's use a shepherd and wolf example. Okay, so you have somebody who is tending their sheep, and there could be or might not be a wolf in the vicinity. So let's say that our null hypothesis is that there is no wolf present. Got it? So you're out there, you're tending your sheep, there is no wolf present. Everything that you would know as that sheep herder would know that you don't have a wolf present. Still with me? A type 1 error or false positive would be crying wolf when there is no wolf present. That is, the actual condition was there was no wolf present. However, the shepherd wrongfully indicated there was a wolf present by calling wolf, wolf. This is a type 1 or false positive error. Stopping there. Okay? What do you think? I haven't hit the type 2 error yet. So the type 1 error is talking about the null, like a false fire alarm, a false alarm on a fire. Okay?
That's just type 1.
That's just type 1, yeah.
So you can confirm that the fire alarm was pulled if there was no fire, so it's not true.
That's what we're going for. Okay? Ready for type 2?
Yeah.
And I think they lead this nicely, and then they're actually going to compare the two because we don't know which one is worse or better, and they're not trying to justify one or the other. Okay, a type 2 error occurs when the null hypothesis is false, but erroneously fails to be rejected. Okay, so a type 2 error is a false negative. So let me say this again. A type 2 error occurs when the null hypothesis, okay, is actually false, but is accepted true by the testing. Okay, a type 2 error or false negative is where the test result indicates that a condition failed while it actually was successful. A type 2 error is committed when we fail to believe a true condition. Talk to me.
So is it like there is a fire, but the fire alarm doesn't go off, and everyone says there's not a fire, but then there is a fire?
That. I smell smoke. There's a fire. I don't hear an alarm.
Okay.
All right, then you trust that there. Yeah, I think
Okay.
I like that.
Okay.
I like that. So,
I think it makes sense.
so a false alarm, no fire present,
Yeah.
alarm went off.
Yeah.
Type 1.
Yeah.
Type 2, there actually is a fire.
Yeah.
But there's no indication.
No, there's not an alarm beeping or flashing or anything, but a fire is actually taking place. Okay? I think we're getting there a little bit better. Do you guys feel a little bit better about this? Because I think I kind of like your reaction so far, and I love it, and it's awesome. Okay, a type 2 error is a false negative where the test result indicates a condition failed while it actually was successful. A type 2 error is committed when we fail to believe a true condition. Continuing our shepherd and wolf example. Okay, so we're going back to the shepherd and wolf. So the last one was, there was not a wolf out there, but the shepherd cried wolf. Okay, that was type 1. So type 2 would be, I think, And if I read this, we'll see in a second if I'm right. So, type 1, no wolf present, but yet shepherd cries wolf. Type 2, there is a wolf present, and the shepherd doesn't say a thing. So I think. So let's see if they verify. Continuing our shepherd and wolf example. Again, our null hypothesis is that there is no wolf present. A type 2 error or false negative would do nothing, not crying wolf, when there's actually a wolf present. That is, the actual situation was there was a wolf present. However, the shepherd wrongfully indicated there was no wolf present and continued to play Candy Crush on his iPhone. And that's actually what it says. I'm pretty sure Shepard's not playing Candy Crush. This is a type 2 error or a false negative error. Okay? Is that clear a little bit? So, in summary for this scenario, lost my page. Type 1 and Type 2 errors are highly dependent on the language or positioning of the null hypothesis. Changing the positioning of the null hypothesis can cause Type 1 and Type 2 errors to switch roles. It is hard to create a blanket statement that is Type 1 error is worse than Type 2 error or vice versa. The severity of a Type 1 and Type 2 errors can only be judged in context of the null hypothesis, which should be thoughtfully worded to ensure that we are running the right test. I highly recommend adding so he talks about a cost assessment. So, if we were to say, what is the worst case scenario, Type 1 or Type 2? It depends on the situation. Let's talk about, God bless you. There is no fire and a fire alarm goes off. We all evacuate and we all say, dang, that was a waste of time. Of course, you're a student going, sweet, we got out of class, right? So you can look at it two different ways. Well, let's say y'all off in college next year. This will happen if you choose to live in the dorms, okay? There are all kinds of fire alarms that will go off while living in the dorms because there are certain people that think it's funny to pull alarms. So you leave the building because the RAs are coming by, getting everybody out, and you're like, oh, man, this sucks, I got to test tomorrow. You get outside, and there's no fire, and then you're mad because there was no fire, and you wasted your time coming out and could have been sleeping. Okay? So that's Type 1 error. Type 2 error. There's actually a fire on the 5th floor. You live on the 17th floor. The alarms aren't going off.
You die in your sleep.
There you go. What's the worst scenario? In that case, Type 2, definitely, because you're dead. Okay? But it doesn't always have to say Type 2 is the worst of the scenarios. Again, it has to depend on your situation. Feel a little bit better about that?
Yeah, I love it.
Okay. I do too. Thank you for letting me go through there. All right. Let's move on to 8.2. Can I do that?
No, can you do an example?
You know what? In 8.2, it'll go through the exact same scenario, but adding just a little bit more. So we'll be totally fine. Cool? All right. Ready, set, stretch. Poke your neighbor in the eye if you need to. All right. Basic goal. Did the results we get happen by chance, or is it something going on here? Okay? So 8.2 notes. Basic goal. Did our results happen by chance, or is something actually going on there? Okay? So the conversation here says, does Princeton have applicants with above average IQs? Okay, Ivy League school in New Jersey, Princeton, do they have their applicants, are they above average IQs? Okay, it is known that the average IQ is 100 with standard deviation 15. So what does that say? What did that just say? What do we know? That next sentence. It is known that the average IQ is 100 with standard deviation 15. Who are we talking about?
People.
People. What people? All. Nailed it. So the whole population has an IQ of this, has a standard deviation of this. So this is everybody's IQ. Not just the people applying to a certain school. That's supposedly everybody. Okay, a random sample of 20 applicants was selected and found that X bar, so the new mean, the mean of the 20 applicants, we have 20 people that were selected, we had 112.37 IQ, and then we had an alpha of 0.05. Okay, hang on. Using alpha of 0.05, can we say that Princeton applicants are above average? One or two tail here? One. Okay? So you're talking about, here's your scenario, here's some average, or this, it's actually that, sorry. And we're talking about this over here. So we're talking about one tail. Okay? So that's what we're going to test. So our null hypothesis, so our null, HO, H naught, is equal to, excuse me, Princeton applicants have IQ equal to 100. What do you think? That's APP, applicants. Okay? No. This is not the null. We'll write the null. We're going to test. Did I say this?
That is the null.
Oh, this is null hypothesis. Sorry. We're going to look at the alternative right now. We're going to test HA. Okay? So this is saying Princeton applicants have an IQ of 100. Right now, what we want to test is what? What do we want to test? No. What do we want to test? Who? What do we want to test?
20 people selected are
People are smart.
Yeah, so we would now want Princeton applicants have IQ greater than 100. That's what that is.
Yeah, but if it's talking about Princeton applicants for the null hypothesis having an IQ equals 100, then why is the alternative one also Princeton applicants? Why isn't it just everyone for the first one?
Okay, we could do that. Do you want to change this? Does this make you feel better?
Yeah.
Everyone? Okay, I'll do that. I think both would be legit, but I like it. Okay. Okay, so everyone has everyone applicants have IQ of 100. I know it's horrible language. I'm sorry. And HA says Princeton applicants have an IQ of greater than 100. We know it's one tail from that because we want a bigger number. We know it's one tail because we drew it up here. So let's work through it. Man, my page. Uh-oh, I just lost myself. Okay. So we're holding off on that for right now. So that was kind of yesterday a little bit. So if the null hypothesis is true, how would we get our sample result? So again, this is what we're drawing right here in that normal curve that's there. Okay, check the three assumptions. I think you can get there. Draw a picture, we can get there. But then let's get to the z-score. That it? That was it. Got lucky. All right, so the z-score looks like too much. Okay, that's pretty ugly to look at. Okay? So this is the type of problem where a lot of students start goofing up math because you're going to rely on your calculator too much. So let's plug in what we know up here. So x bar is 112.37, which we had stated here, right? That was our Princeton folks. And then mu is 100. That's what the whole population of everybody's IQ average is. over the standard deviation of everybody divided by n. And n is how many people we're talking about? 20. Square root of 20. There we go. So if you do this math, see if you can make this work. I worked it out for you, but see if you can make this work on your calculator. I'm going to get a z-score of 3.69. Okay? So a z-score of 3.69. Remember, a z-score is kind of another name for what? But it uses decimals. It's like a standard deviation. So if I were to draw my picture, this would be 1 standard deviation, here would be 2, here would be 3, here would be 3.69 standard deviation. Okay, we're 3.69 standard deviations above the average. Pretty far? Yes. All right. Now what we want to find here is this area. I want to find that area. Okay? So I'm going to use NCDF on the calculator. Remember, NCDF, we don't have to worry about going 1 minus, because your z-score, if you went to your z-table, it would have given you the area to the left. But if I use NCDF on the calculator, it can give us whatever area. So NCDF, if you remember, you have your lower limit, comma, your upper limit, comma, your 0, which will be your average or your mean, and then 1, which is your standard deviation. Okay, the reason you're using 0 and 1 is you're not going back through to find everything up there. So, if I use the NCDF, my low is going to be the 3.69. My high, I don't know, make this bigger, make it 1,000 or whatever. And then 0, 1. Okay? And the reason why I'm using this is because I'm basing it off of 3.69. I'm not going off the mean that's up there and finding the standard deviation. I'm not doing that. So if you plug this into your calculator, the area to the right of there up top is going to come out to do you agree? It's second bars under there. Okay. So this becomes our new p-value. And if p is less than, these are our two tests, p is less than or p is greater than, here we reject the null, and here we fail to reject the, so this means that we will accept the null. All right, now wait. We just got into lingo that we're not happy with. So let's see. We're going to figure this out in a second. And one of these is going to go with type 1, one will go with type 2. Ready? Is my p-value less than my alpha? Is my p-value less than my alpha? So my p-value is less than alpha. So I reject my null. Everyone, applicants have an IQ of 100. I reject it.
So those are your type 1 and 2.
Hang on, we'll get there. We gotta get down a smidge further, but you're getting onto it the right idea. So if a p-value is less than our cutoff alpha, in this case it's 0.05, we reject the null. Okay, if p-value is larger, we fail to reject the null, so we put the conclusion in context. So, if p minus the value is less than alpha, we reject the null. If P minus the value is greater than alpha, we reject the null. Let's see if we continue that to the next page. No, it scoops things up. It doesn't go any further than that. Yo.
So because you proved the first statement proved true. The null, which is everyone applies to I have an IQ 100 is false. That's the issue. It's false.
Everyone has an IQ of 100. We have rejected because of this false.
Where'd you get the 0 from 1?
Oh, okay. Because we're using a z-score of 3.69, which means as far as our standard deviation is positive, that means it's 3 standard deviations to the right. So if we're not worried about actual values, the mean will be 0, and then 1 standard deviation, -1. +2, -2, +3, -3. So that's all we're going with. So that's why we're using the 0 and the 1, because we found the z-score. The z-score is the actual standard deviation. That says that we are 3 standard deviations above the mean. But we're not classifying our mean up here as 100 or 112.37. We're just going back to the finding the actual area, saying this is where our z-score falls in order to get us that area. That's all it is. Is that okay? Yeah.
For the NCEF, it's for like P actually equals 0.000112.
112. Ooh, I was even further.
It doesn't matter.
Did you finish? Wait, was that your
Perfect. Huh. Can we move on? I got 3 to 1 that the Tempe twins over there don't stop talking for this next example. What? No, don't worry about it. We're just over here doing math. Can we do an example 1? We want to know if Greek students spend more time on extracurricular activities than other high school students. A national organization recently claimed that high school students spend an average of 11.6 hours a week on extracurriculars with a standard deviation of 4.2 hours. We sample 50 Greek students and find that they spend an average of 12.8 hours a week on extracurriculars with an alpha of 0.05. Can we say that Greek students spend more time on extracurriculars? All right, can we go through it? Okay. Now, from my perspective, being here at this school, I'd say there's an awful lot of you that do a lot of extracurricular activities. I have been at schools where that bell rings at the end of the day, the campus becomes a ghost town. There's nobody on the fields, there's nobody in the theater, there's nobody in the gym, nobody doing. It's like, hello, hello, hello. And then people are going, what are you still doing here? It's 2:30. Why are you leaving? So, all right. So they feel that all high school students spend this much hours per week extracurricular. Standard deviation of everybody is this. We sample 50 Cherry Creek kiddos, and we have found that because of our sample, because of our random selection of 50 kids, that we found 12.8 hours. You're always my kids. I'm sorry. Okay, so spend more time on extracurricular. Spend more time on extracurricular. 1 or 2 tail? 1. So basically, we're looking at this scenario. 1 tail. We'll fill it out when we get there. Okay, that's what we're looking at. It's a 1 tail scenario. Okay, now guys and girls, I didn't tell you this, but the only difference between 1 and 2 tail is as you get down towards the end, you multiply your p-score by 2 if it's a 2 tail scenario, because the normal curve is symmetric about itself. Okay, all right. All right, they tell us we have this, and we're going to test this. So we're looking at a 95% confidence interval. So first thing we want to do is we want to find the z-score. Hey, here's a question for you. Let's say that this was like our last problem, it was less than 30. Why are we still finding the z-score? Still last chapter. What do I know? Standard deviation of what? You're absolutely right. Of the entire population, not just your selection. Okay? So that's why we're using the z-score. All right, so our z-score is going to be 12.8 as our Creek kids versus everybody over 4.2, the standard deviation of our entire population, over the square root of 50. And if we do this math right here, this is going to give me 2.02 as a z-score. 2.02. So 2.02, you're talking about you are more than 2 standard deviations above the average. Okay? We're more than 2 standard deviations above the average. Okay? So you have if that's 0, you have 1 standard deviation, you have 2 standard deviations. So we are at 2.02, excuse me. That's basically what we're looking at. We're talking about area to the right. It's one tail. Let's find our p-value. But we're going to find our p-value using our calculator. So this is your NCDF. And we're going to go, we're looking to the area to the right. So my minimum value will be my z-score of 2.02. We'll raise that to like 1,000 or 10,000 or 1,000,000. I don't care. And then we have a standard deviation of 0 because we're normalizing it. And our standard deviation is 1. Okay? Oh, you know what we forgot? Duh. We're over testing stuff. We don't even have this important stuff. Okay. So what can we test? What are we testing here? What should our null hypothesis be? So, something like this maybe? 11.6 hours on extracurricular. Or, that should be a question mark. That's a big period. Okay, and then, what's this one? Is that okay? I'm sorry, I meant to write those in earlier. I apologize. Okay. So, make this right. P is less than alpha. I'll just get away from the fail to reject. That's a term that not everyone likes. All right, my p-score is what? 0.05. What is that? Point what? 0.021. So 0.021. And what's alpha? 0.05. So is that a true statement like that?
Yeah.
So what do? We reject our null. All students spend 11.6 hours. Huh. You want to accept it?
I think it's 0.2.
So we could accept? You want to accept HA?
Yeah.
Okay. What do you think, Creekers? You guys think you spend more than that? Could be. Again, it's a made-up problem, right? But I think as a school, and the thing is, most of you won't see this now, and I hope that you guys when you grow up and you become big people, and you decide to have kids or adopt kids or however you want to go about kids, kids come through here and you can have them. Because I think that'd be kind of cool. But what you might see is if you move to a different place, a lot of things you will refer back to your high school is, gosh, at my high school I remember this. And so hopefully you had a wonderful experience. I realize there's things that are silly sometimes, but it is what it is. Hey, what time are we out of here? And don't lie.
102.
102. All right. So, do what?